Great. Well, why don't we go ahead and get started this morning? I'm Matt Russell with the University of Minnesota. This is the Technology and Forest Carbon webinar series. I see some familiar names in the list that have been joining us for this whole series this week. So welcome back to those of you that have joined us this week, and welcome to the new folks that are joining us for this webinar series. This webinar today and all this week has been sponsored and brought to you by the Sustainable Forest Education Cooperative and the University of Minnesota Extension. Based at Eli and I are based here in St. Paul and at Cloquet Forestry Center. We're really appreciative of support from the Minnesota Forest Resources Council to help bring this webinar series and a number of other workshops and webinars that we've done this fall focused on forest carbon and what it means for land managers and forest landowners going into the future. So welcome everyone. As I mentioned, this is the third in our three-part series for this webinar series. On Monday, we heard from the Nature Conservancy about some new products that they've developed on reforestation opportunities with a focus really on Minnesota and Wisconsin. On Wednesday, we heard from folks from NCX. That's a carbon market kind of a project developer interested in bringing some of the measurements and machine learning and artificial intelligence technologies to carbon markets. So it was great to hear from those folks. And then today, I'll introduce Chad here in a little bit, but we're going to talk about better understanding the uncertainty of some of the forest carbon estimates that are provided. And Chad will go into that here in a bit. I will say too that we have these recordings available. These recordings are available on the SFEC's YouTube page, and we can be sure to get you a link to these recordings if you registered for the event afterwards in a follow-up email. In terms of how to post questions, those of you that have been a part of these webinars before, you know that we like to use Slido. Slido, once you click on that link, it will open up in your web browser, and then you can ask questions there. And the thing that we like about it is you can also upvote questions. And so if you see a question that you really like and you want answered, you can hit that, I think it's a thumbs up button right there, and that'll let us know that there's a lot of interest in that question. You can also reply to questions, which we found really valuable. People can add their own insights into a question that might be provided there in the Slido system. And so I'm sure that Eli probably added that link in the chat by now. And so that's what we're going to be using today to help get through questions for Chad as we go through the morning. And so I'm going to go ahead and click stop sharing, and I'll ask Chad if you want to go ahead and share your screen with your slides. And for a quick introduction of Chad, Chad is an assistant professor in remote sensing based at the Department of Forest Resources here in St. Paul. And he's going to talk to us today about accounting for uncertainty in biomass maps across the US. So Chad, you can go ahead and take it away.
All right. Hello, everyone. So the title of the webinar today is either understanding or accounting for uncertainty in above ground biomass or carbon maps for forests. So I end up using, a lot of times I end up using this above ground biomass and forest carbon or interchangeably, just because they're so closely related to each other. So sometimes you might hear biomass and sometimes you might hear carbon, but we're kind of getting at the same thing. So let's see. First, a little bit about me. As Matt said, I'm starting my third year as a remote sensing and geospatial analysis professor at the University of Minnesota Forest Resources, and I have a background in education in forestry, geography, and statistics. And for the past, well, I guess my entire research life, but still fairly new yet, I guess. But most of the work that I've been working on has been through a project sponsored by NASA's carbon monitoring system. And the goal of this project, this large overarching project, is to develop prototypes for monitoring, reporting, and verification systems for terrestrial carbon stocks and fluxes. So that all just means that I spend a lot of time making maps of forest carbon and forest biomass, And I tend to, and I focus a lot of my my projects on dealing with and characterizing uncertainty, so that we can incorporate these types of maps in estimation routines, so that we can get statistically robust or rigorous estimates of forest carbon or biomass. That's kind of what motivates why I am doing what I do, I guess. So I'll start by briefly talking about kind of, I guess, the more traditional way to try to estimate forest carbon using field samples alone, and then we'll see how we can potentially bring in remote sensing information to be able to improve those estimates, but still kind of try to stay in the realm of, you know, being statistically rigorous, I guess. So for those of you who don't know about the FIA program, so the U.S. Forest Service Forest Inventory and Analysis Program, they have a large, a very extensive network of field plots that cover the entire U.S. So all these little gray points are fuzz locations of FIA plots. And then they cover all forest lands. So they're on public and private lands. And then they can use these, the information they collect from these plots to develop estimates of many forest inventory parameters that we might be interested in. But here we're interested in forest biomass. So these plots end up getting revisited every 10 years, at least in the west, on the west, and then it's usually every 5 or so years on the East Coast. And then it's kind of a mix in between. But so this is a probability sampling design, which means we can use what we term as design-based type estimators. So when we actually go in and estimate forest carbon using these plots alone, and develop a standard error and a confidence interval for them, we can safely interpret those as being valid. So the California Air Resources Board relies on the types of protocols that the FIA has established, and the growth and yield models that they use for projecting plots forward in time to be able to assess forest growth. So we really like this design. It's a very robust system for estimating lots of forest inventory variables, including forest carbon, but there's some pitfalls with it as well. So here's an example plot. They have 4 little subplots that go around this larger plot area here. And then on this plot, they're taking measurements of trees. So taking diameter measurements and then also height measurements of trees, and then they apply allometric equations to be able to estimate the amount of carbon in particular trees, and then they can sum up or average the amount of carbon within the plots to be able to scale it up to a plot level, and then we can use those to generate our estimates. And then every 5 or so years, the FIA program puts out a report. And then usually it's the first 10 or 15 pages are these really nice figures where they explain how the forest has been changing over the past 10 or so years. And then the remaining large amount of pages end up being just tables where they tell you how much, where they split out everything by different classes and be able to just generate a whole host of estimates to tell us about the forest in these particular areas. So the FIA is great at generating estimates at like a state level or for national reporting, but it's not really very good for smaller scale estimates. So if we wanted to estimate things at the county level or a stand level, which is usually kind of where we want to hang out, if we're interested in getting small landowners into carbon trading programs and whatnot, we really need to be able to kind of scale down and be able to operate at the level of a forest or an ownership boundary, and not necessarily at these large state or national scales. It's also not that great at getting annual estimates. So there's they have a rotating panel system is how they term it, but each one of the only 10% or so of the plots are measured each year. And then usually, especially for smaller areas, this means that they have to aggregate these plots that are measured in different years to kind of get average estimates for the past 10 years or so. So being able to look at estimates annually is also pretty difficult using the FIA data alone. So the natural question is, how can we incorporate remote sensing information to be able to improve these estimates so we can go to smaller scales? And then that unleashed a whole, then there was a whole host of research efforts that have been dealing with trying to figure out how to bring remote sensing data into the estimation approaches that the FIA uses to be able to estimate forest carbon. There's a couple example maps. So this one here on the left, this was developed by the FIA. They use a machine learning algorithm to relate plots with, I believe it's mostly Landsat-based remote sensing data for this one. And then they're able to generate these maps at a 30-meter scale. And then in the last webinar, we learned about the natural, carbon exchange, I believe, or natural capital exchange, their base map. So they've generated this map using artificial intelligence where they're able to make predictions of whatever forest carbon type inventory variables that they need to make estimates for all the pixels that they're trying to monitor. And then there's it's getting to the point that there's so many of these biomass and carbon maps out there now that people are writing papers just comparing the different maps. So there's this is just 4 different maps using 4 very different methods and very different data sets. They produce different predictions of biomass in these different spots. So the question starts to become like, which map should we use? Which one is more accurate than the other? Should we be relying on maps that use particular field measurements to be able to calibrate the models? Should we be using different model types that allow us to maybe look at estimates differently? But there's a whole host of questions on like essentially what we should do with these maps now that so many of them have been generated now, to be able to assess which ones to use and how to use them to actually come up with, you know, an estimate of forest carbon for your stand. Yeah, so how do we use these maps to estimate forest carbon? So when I'm thinking about trying to figure out how to use a map like this to incorporate into a forest carbon estimator, these are a few of the things that I'm thinking about as far as things that I would like to see in a product and in a particular estimator to be able to, I guess, decide that it would be most useful. We would like to see these biomass mapped. So we want to see these predictions in space. It's really helpful to see the spatial distribution of biomass and carbon so we can make management decisions based on what we see and how things are spatially distributed. We would also like to see some uncertainty, at least at the pixel level. And then that uncertainty should reflect the amount of data and the quality of the data in the area that we are predicting now. And then what's important here, and what we'll focus on quite a bit here in this first case study, is a lot about scaling estimates to term arbitrary aerial units. But that's essentially we're trying to get from pixels to stands, and then potentially to counties and then states. So we're just trying to figure out a way to be able to estimate carbon for an area rather than just for a pixel, but we want to be able to get uncertainty for that aerial unit as well. And we won't touch on it too much today, but I also think a lot about trying to figure out how to propagate uncertainty from these estimates into subsequent analyses. So maybe once we have a map of forest carbon, how do we take the, knowing that that map isn't correct, how do we propagate that error through a model maybe for something else we might be interested in, but still acknowledge that that forest carbon map that we are relying on still has uncertainty in it. With that, we can hop into a study here. My grad student, Ethan Emick, and I have been working on this project quite a bit over the past couple of years now. So this is a NASA carbon monitoring system project. And this project was done in 2 phases. So in the phase 1 portion of their project, they developed some above ground biomass maps for Oregon, Washington, Idaho, and Montana and then I believe California too. And then they produced these maps for the year 2000 through 2016. So to be able to produce this map, they asked everybody who had field plots and airborne LiDAR data sets in the area to donate these data sets so they could develop a very large machine learning or a random forest model to be able to predict biomass using these airborne LiDAR data sets. And then once they produced all these maps for the areas where they had airborne LiDAR, they took those predictions from that machine learning algorithm and then passed them through a second model where they linked it to Landsat time series data. So that's our Landsat imagery, where we have it at a 30-meter scale, and then each pixel is visited every 16 or so days. So using this large time series, they're able to make annual predictions based from 2000 to 2016. And that's all. But that second model is based completely on predictions from this first model. So you can imagine that there's going to be an issue as far as there's going to be uncertainty pertaining to this machine learning model. And then once we pass it into the second model, we're effectively assuming that these random forest predictions were observed, were essentially perfect. So we're ignoring the uncertainty in this first stage model, and then it doesn't get propagated through to the second stage model. So there's going to be some issues likely dealing with potential biases and things like that that we likely have to take care of now that we have this map if we want to actually get an estimate from it. So knowing that none of these pixel predictions are perfect, we're going to make an attempt here to recalibrate this map using the FIA field data, and then we'll do that within a regression model. And then we're going to try several different estimation approaches that all either fall within a design-based or model-based realm of statistical inference. So we can hopefully assume that our estimates of uncertainty for the pixels and the areas that we're going to end up generating are statistically robust. So that, meaning that if we actually produce a 95% confidence interval, we can assume that it's if we, I guess, under repeated sampling, that as we produce more and more of these confidence intervals, most of, or 95% of them would contain the actual amount of carbon in that particular area. So this is my first math slide. I promise you there's only one more, and I won't torture you too much with it, other than we're going to look at a few different estimates here. So I want to define what I mean by a direct estimate here. So my X1, those are just those predictions. Those are just those mapped predictions. So, and my Y over here, these are those field-based estimates of forest biomass based on the FIA data. So essentially all we're doing is we're going to take an average of the pixel predictions for a particular area, and then just assume that that estimate is the same thing as what the FIA is measuring. So we're not including any FIA data at all in here. We're just generating estimates based off the map. And then we have two other estimators here that exist in a design-based, or sometimes called a model-assisted framework. So this one, this orange one here, this would be just an estimate of how much biomass is in a particular area based on the field, based on the FIA data alone. So we can assume that this orange one here is essentially how the FIA currently does things without using any remote sensing data at all. So this is only the remote sensing data and then no remote sensing data. And then we also derive a particular estimator that exists in this design-based realm where we can bring in the phase one predictions within a little regression model here and be able to essentially incorporate our phase one predictions, but still kind of exist in this design-based or model-assisted realm. So we can calculate standard errors and things like that. And then we'll also look a little bit, and then we'll be testing a spatial model. So this is in a model-based realm, but we still have our mapped predictions in our regression model here. And then we're calibrating that to the FIA data. But we have this special spatial random effect in here that's designed to, sorry, the people outside the door, that's designed to absorb any spatial autocorrelation that might exist after fitting the model. So hopefully that we can safely assume that these errors here would be independent and identically distributed. So if we can assume that those errors are like that, then when we generate confidence intervals for our estimates, we can safely interpret them. So here's our first crack at a state level estimate for the state of Oregon using these two data sets. So using the FIA data and this above ground biomass map, the first thing that probably sticks out quite obviously is that the direct estimator, so the one that doesn't include any FIA data at all, so this is just an average of all the biomass pixels for the state of Oregon, you can see that it's a lot higher than any of the other estimators that we tried out. And considering that the FIA is our orange estimate down here, we can, it's probably pretty safe to assume that there's a lot of bias in the above ground biomass map that was produced. But then we can look at our model assisted estimator, which is, exists in our design-based realm again, but is incorporating that map data. And we can see that that ends up bringing down our estimate more in line with what the FIA is telling us. But these little bars here are my 95% confidence intervals. And we can see that they end up being usually a little bit narrower than the design-based estimate all on its own. So this is indicating to us that even though there's bias in this map, and even though there's a lot of uncertainty that exists inside of it, we can incorporate it within this model assisted framework and be able to generate estimates that are at least a little bit better than the design-based estimates that the FIA might use. And then we also have our spatial model estimate, spatial model-based approach, and we can see that they tend to, it tends to be similar to that model-assisted approach at this scale. So we've got estimates from 2001 to 2016 here. And these little ends up here, this is the number of plots within the state for the year 2001. You can see that they change slightly, but they all kind of gravitate around, it's like between 850 and 700 or so. So that's great at the state level, but what about drilling down maybe to a county level? So here's a particular county here, and we can see that the sample sizes get a little bit smaller. They're still pretty large. We're looking at things close to 100 here. But we can see that our estimates, it tends to be that our model-assisted estimator likes to behave a little bit better than potentially that model-based approach, and definitely better than the design-based approach at this point. We're getting narrower and narrower, we're getting narrower confidence intervals within that model-assisted estimator when we're looking at samples like this, at least for this particular county. It changes from county to county, but it kind of works that way. And then we can look at a county with a little bit lower sample size. We can start to see that those design-based estimates are starting to get pretty wide. Because this is a pretty low sample size to be able to calculate biomass. And actually there's 30 tends to be the limit that the FIA kind of says about as far as calculating FIA estimates for areas. But we can see that there's a lot of uncertainty about what's going on when our sample size is so small. And then we can see that model assisted estimator is in some years, it's working out better than the design-based approach, but in other years, it's not helping as much as it might want to, as we might have seen when we had larger sample sizes. However, we start to see this spatial modeling approach starting to win out, and this is likely because we're able to borrow strength from neighboring counties and neighboring areas to be able to inform predictions about our predictions of what's going on in the particular county due to that spatial random effect that we have in there. And that's likely what's helping us get much more reasonable estimates that we can rely on a little bit more, even though our sample sizes are smaller. And then once we go to sample sizes that are incredibly small, so we start looking at areas that maybe only have 4 or 5 or 7 or 8 FIA plots in them, we can see that that spatial modeling approach ends up being a clear winner. And then I also went through and Ethan and I went through and plotted out essentially for each county. We plotted the number, or county year combination. We plotted the number of samples versus the width of that uncertainty interval. So we can see that as when we're looking at really high sample sizes, so that's counties with a lot of FIA plots in them, so between 60 and 90 or so, we can see that all these approaches do behave pretty similarly. Sorry, I switched my colors here. The design-based approach is the green one here, and then the model-assisted is orange, and the geostat model is purple here, which is the spatial model. We can see that that model-assisted and spatial modeling approach behave fairly similarly once we start getting out past 60 observations, and they tend to beat out the design-based estimator. But then when we start getting into smaller sample sizes, we can see that that spatial model is definitely performing quite a bit better as far as being more certain or more confident in our predictions or estimates than the model-assisted or the design-based approach. And we also get a lot more variability when we start looking at lower numbers of samples too. And then we can drill down just a little bit further. So these are hexagons that were established by the FIA. These are considered to be the smallest aerial unit that you can actually get an estimate that you could rely on from the FIA data alone. So we wanted to look at these. So there's actually about 30 or 25 to 30 plots within each one of these hexagons. And that's kind of the limit on the sample size that we usually talk about when we're talking about design-based type estimators and things like that. So here we used our spatial model. So we're not going to look at the design-based or model-assisted approaches here at the annual scale because the sample sizes were just too small inside the hexagons at an annual time step. So there's usually only like 3 to 5 plots within each one of these hexagons per year. So we can see that we get a map, we get a nice map of biomass here, and then we can actually calculate that uncertainty based on our posterior distributions from our spatial model here. And then we can compare that to estimates on the FIA data alone. Again, these are 10-year pooled estimates though. So you can imagine this is like an average over the past 10 years about how much biomass is in a particular area. And if you kind of go back and forth, we can see that the maps are somewhat similar. We seem to be getting, it seems to be, the spatial model seems to be quite a bit smoother. But that's probably because it's borrowing strength across locations. But the uncertainty is pretty interesting. So we've got particular hexagons here that have really high uncertainty, probably because there was a lot of variability in the 30 FIA plots that existed in there. Whereas when we look at that pixel from here, we're actually borrowing from neighboring FIA plots to help inform our prediction locally, which is probably why that uncertainty is coming down. So some takeaways from this first approach here. So these direct estimates using only those phase 1 predictions, they definitely seem to be biased. And then actually bringing in that field data and then using a design-based estimator or a model-assisted estimator helps to remove that bias and then give us more reliable estimates. And then the spatial model-based and the model-assisted estimates of biomass at the state level, they tended to have somewhat narrower intervals than using just the field data. And this is indicating to us that this biomass map is actually helping us improve these estimates. And then we noticed that the spatial model, it definitely won out when our sample size, when our field sample size was very small. And that's likely because we are borrowing strength across locations. And then remote sensing aided spatial model-based estimator. And this might allow for more robust annual AGV biomass estimates at small scales with this FIA data. So yeah, so I made an attempt. So Ethan and I worked up a way to make this spatial model based estimator. We generated a, I'll click on it here. Well, hang on. I'm actually can we copy this? let's see. You guys seeing my there it
Yep.
is. Okay,
Yeah,
sweet.
looks
Cool.
good.
All right, cool. Yeah, so we went through and we built a spatial model, and instead of using a biomass map that's maybe potentially already been created here, we just used the statewide LiDAR collection, and then we used the 400 or so field plots that exist at Cloquet Forestry Center, and then just built a regression model with the spatial random effect. And then our goal here was to be able to use a product like this to be able to generate estimates kind of on the fly for small areas. So we can, if we look at a large area here first, we can grab this whole thing. And then it's going to take a second, and then it's going to generate an estimate of above ground biomass density and total biomass for Cloquet Forestry Center using that spatial modeling approach. So we get a confidence interval, a 95% confidence interval here. You might be able to see it on these little dashed lines here, but so that's using the same approach that we were talking about for the Oregon data set. So it's a lot smaller scale. It's a little more fun because it works out a little bit faster because it's not dealing with quite as much data. But yeah, so one of the ideas that we would be great is to be able to expand this out to be able to incorporating FIA data for Minnesota to be able to produce this map at the state level. So if we can zoom in here a little bit and get a feel for how things are working, so we can pick a larger area like so. And I think it did it. Okay, so we can see that our confidence interval is looks like around 36 to 42 for this size area. But if we actually go in and do a much smaller area, just grab a few pixels, you can see that that confidence interval gets a lot wider. Which is a pretty sensible result. We would expect to be more confident in the average for a large area than the average for a smaller area. There's going to just be more variability in smaller areas than we would expect at larger areas. So we're getting somewhat sensible results as far as like what our uncertainty is saying, and all those things. And it's a fun little map to just play around with. This web link is live. I think, yeah, now I can grab it. You can post it in the chat here, and then you guys can play with it if you wish. So that's the end of my first round of things, but it looks like we're already at 35 minutes here. So I'm happy to start taking some questions if we have any.
Yeah, it looks like a number have come through. I'll turn it over to Eli to help moderate those questions.
Great. Thanks, Chad, for the presentation. I am getting myself set up here. I'll remind folks, as if you're watching the chat, you've seen me say this before, but I do encourage folks to go and check out those questions. You can add new questions, thumbs up existing questions, which helps us to know which ones to ask, and so on. Oh, and I need to share my screen. Chad, I'm going to take screen sharing from you for just a moment.
No, that's fine. Yeah.
All right, so I think you're seeing my screen now. First question, Chad, it seems that there's considerable bias based on the direct estimate from the machine learning model compared to the FIA data. Does this not suggest that the machine learning model is not very good? Should you use a different type of model? Thoughts on that?
Yeah, I do think it suggests that the model isn't all that great. But I think that a lot of time, like with most of these approaches where we're trying to like send it. So we like these machine learning models because we can bring in so much information and then kind of quickly parse through it to be able to generate, I guess, the best estimate we can get based on, potentially hundreds of explanatory variables. So, but what happens kind of at the end of it is that there tends to be, depending on the field data we're using to calibrate it, or the relationships between those remote sensing variables and the particular field data that we're working with, we can end up with a lot of bias here. But I think what this emphasizes is that we should probably assume that there's going to be bias and a large amount of uncertainty in a lot of these types of maps. And we need to be thinking about that before we try to actually go in and generate an estimate. So the idea of like being able to recalibrate a model, a map like this, using field data that's consistently measured in a way that's been vetted and used for years, it helps us be able to account for that bias and then correct for it to be able to get our estimator. But if we managed to get a map that didn't have any bias in it, it would likely be when we actually use it in this this kind of calibration framework we're talking about here, we should see even larger reduction in uncertainty. So we would be more confident in our estimates.
Great, thanks, Chad. Next question: what role does the Forest Service play in reviewing, critiquing, recommending, and ultimately adopting different methodological approaches for analyzing FIA data to maintain consistency across states and for national estimates?
All right. Well, so the Forest Service, the Forest Inventory Analysis Program, they're responsible for setting up the protocols that we use on FIA plots to make measurements. And then we have this wonderful green book that establishes all the estimators that the FIA uses for calculating everything. And then this is all consistently used across all the states. So the Forest Service tends to be they're the ones who establish how to estimate things with the FIA data, and then a lot of other agencies end up adopting their particular protocols to be consistent, and also because it's a very robust way to do it.
Great. Can the spatial models be adjusted to calculate total forest carbon, AGM plus soil carbon and below ground biomass?
Definitely. Yeah, so it just depends on what you end up using as your Y in your model. So here, the Y in our model was above ground biomass, but that we could easily calibrate it directly to above ground biomass plus soil carbon plus below ground biomass. What's even a little bit more interesting though is that these spatial models can be extended into what we would say is a multivariate spatial modeling framework, where we can actually predict multiple Ys at the same time, accounting for cross correlations between the different carbon pools. So you could have one model that simultaneously predicts above ground biomass, below ground biomass, and then any other parts that you'd be interested in, and that would jointly predict all these things for your small areas or for mapping.
Wow.
Yeah, it's just a matter of getting a computer that's big enough to fit these things.
Yeah.
So
next question. I don't understand machine learning models well, but my understanding is that the fit models are kind of black box. If that's the case, how can one possibly propagate error through them? This is something you talked about kind of early in the talk.
Yeah, that's a great question. So I have some familiarity with random forest, but yeah. So when we're coming out of random forest, which is definitely a black box machine learning algorithm, they do have this kind of voting system where they're fitting multiple decision trees, and then they're able to kind of get at uncertainty in their predictions at pixel levels that way. But the type of uncertainty that we're getting based on these votes is not the same thing as like a 95% confidence interval that I was talking about with the particular models here. So it becomes really difficult to try to propagate error. We got around that by recalibrating the map to the FIA field data, and then using essentially the lack of fit between the FIA data and the remote sensing product, or the biomass map, to be able to assess uncertainty of our estimates. But I have seen a couple approaches where people will try to take a machine learning algorithm like random forest and then embed it inside of a probability model. where you can get more statistically, I guess, rigorous estimates of uncertainty through there, which is actually, they look pretty interesting. It might be a new way forward as far as incorporating machine learning, but still trying to get interpretable confidence intervals and things like that from our predictions and estimates.
Next, what causes year-to-year difference in average biomass estimates using remote sensing data where FIA estimates were pretty similar?
It's likely depending on how well the remote sensing data is fitting the field data locally in particular areas. So, I mean, just based on natural variability and I guess in the FIA plot estimates, measurements versus the remote sensing data there locally. For instance, you might have, maybe there was a point where the Landsat data said this pixel was really, really green. There wasn't actually any forest there. Maybe it was grass. So there's going to be discrepancies based on the remote sensing data isn't going to be perfectly related to what's going on the plots, and then you might start to see that show up like you were talking about.
Great. A couple more here. And then I know, Chad, you've got some more content. You can make the call whether you want to present that if it fits or what. Next question is, how does your CFC example, Cloquet Forestry Center, compare to the canopy surface map for the Forestry Center?
So the canopy surface map, that was, I don't think I've actually seen the canopy surface map at this point yet. I'm actually not exactly sure, but the CFC map does measure, I mean, that's attempting to estimate above ground biomass. So it's not, we're not estimating canopy heights there. We are taking LiDAR derived canopy height metrics, which is maybe what you were considering when you were talking about canopy surface map. But we use that as an explanatory variable to predict biomass in the area.
Yeah, there was another question about that I archived because it was somebody had replied to it. I'm not sure if Ethan is on the call doing that or who that was, but
yeah.
That one seemed to be resolved. And I think the response was 95th percentile height based on that LiDAR estimate.
Yep.
Okay, are these methods robust to missing data or outliers? For example, FIA puts a minimum size threshold on trees for biomass estimation. They don't always get access to private land and so
on. These methods would be as robust to missing data and outliers as the FIA estimators themselves, I guess. So we are relying quite, with this, we're relying quite heavily on the FIA data being a sound, I guess, probability sample. And so missing data from FIA plots and, if we don't, so if we're denied access to particular private lands or anything, that might bias that FIA sample in and of itself. And that's definitely going to end up being reflected in these outputs that we have here.
Yeah. A couple more questions. Based on your work with spatial model uncertainty, what are your thoughts on using remote sensing and spatial models to calculate carbon for actual carbon contracts?
I think it's a great idea. I like that we, so for a small forest landowner, being able to enter into a carbon market, usually a lot of times it's the upfront cost of actually inventorying your land that ends up being prohibitive. So a lot of small landowners can't enter these markets because the cost of monitoring your the actual carbon on your forest costs more than anything you'd be getting from carbon credits. So this approach could hopefully let us leverage FIA and publicly available remote sensing data to be able to hone in on better estimates locally for smaller lands, and would hopefully allow small landowners to be able to enter these markets with less of a cost barrier. But I'd love to see it. So
Yeah. Chad, you talked about some data in Oregon. What were the predictors in the spatial model for Oregon? Was the spatial model random forest?
The spatial model wasn't random forest. It was a Bayesian kriging model that used the map predictions as an explanatory variable in the regression framework. So the random forest model was fit using crowdsourced data sets to be able to produce the initial map. And then we went in and took that map and then recalibrated it to FIA data. And that was just a simple spatial regression model. So it was just one covariate, and that one covariate was the biomass map.
Okay. And the last question for now, do you consider only the central subplot or all 4 subplots while relating field data to remote sensing data?
For this one, we've been considering, we considered all 4. So we, all 4 subplots constitute one plot. That's our one independent sample of that particular forest or area. But it is a challenge, definitely, being able to link 30-meter gridded remote sensing data to these FIA plots that are essentially kind of discontinuous small networks of subplots. But it's based on the data that's available, it's kind of what we kind of have to end up doing here at this point. As far, like, I still really like the FIA because the FIA just has such a nice sampling design. The idea of then going in and developing an entirely new sampling design that matches to fit with remote sensing observations would it probably end up being quite costly. But I think there are people working on figuring out how to maybe adapt the FIA protocols to be able to kind of line up a little bit more with remote sensing objectives. But yeah.
All right, well, Chad, thank you. With that, I'm going to stop sharing my screen. We're at 9:47, and up to you how you'd like to proceed. I know you had something else you wanted to talk about. Not sure if there's time left or what.
I mean, I can walk through a few slides. So the next part of the talk was going in and looking at how to some more work that Ethan and I are doing about figuring out how to bring in sampled remote sensing information that might be cheaper to collect than actual field data in a forest to be able to essentially, if you could imagine that if you owned a forest stand and then you went in and looked at this spatial model output or whatever, and then you found out that your uncertainty was still way too high, and you needed to bring in additional data to be able to hone in your baseline estimate of forest carbon. How could you do that with potentially some sampled remote sensing information? So it kind of fits, and I can do it real fast, and then there it is. All right. So yeah, so we recently invested in a terrestrial laser scanner here at the University of Minnesota, and then what this thing is essentially a LiDAR sensor. So this is my student Ethan out there in the Mueller property out in Wisconsin. So this TLS scanner here, essentially we can put this in the center of a plot or a subplot, and then this thing is a LiDAR scanner, so it shoots points and spins around in a circle, and then all those points end up being bouncing off of particular trees within the plot or whatnot. And then there are a few algorithms that have been developed where they can go in and essentially look at these point clouds for trees on the plot, and go in and try to actually estimate what the diameter of the tree is and basal area, and then also try to estimate tree counts based on this instrument alone. So what we were interested in doing is seeing if we could actually use this terrestrial laser scanner to augment a field sample, a field inventory, to be able to improve estimates while being able to measure while measuring fewer plots with traditional field methods. So this is the what we've been calling the Mueller property. So it's it's about 160 acres in Wisconsin. It's about an hour or so from the St. Paul campus. And then we went in there and we established a whole bunch of FIA style plots. I think we had what, 1, 2, 3, 4, 5, 6. We got, I think, almost 30 of them in there. Yep. So, but what we're going to do is for let's see, for 10 of them, we're actually going to go in and measure at each subplot. We're going to go in and measure trees in the traditional way. So grab a DBH tape and then identify the species and then use allometric equations to be able to calculate biomass for those plots. But on every one of these plots, we're going to run this TLS scanner and collect that TLS data. And then we can use an algorithm to try to guess at how many trees per acre or how many trees were on each plot and get basal area and all those things. So the trick is trying to figure out how to come up with an estimation approach that allows us to incorporate this sampled. So when I say sampled, I mean that TLS data isn't wall to wall, so we don't have it everywhere. So we can't make predictions of it everywhere like we would with a traditional map. But we can still come up with a way to be able to incorporate this extra information from these extra plots and then hopefully improve our estimate, even though we're only using 10 field plots. The idea being that collecting the TLS data should be a lot faster and cheaper than actually collecting all the inventory data we need on a plot. So it's a cheaper way, hopefully, maybe, to improve our estimates. We also have some wall-to-wall data here. So we have some imagery that was collected using a drone, and then we can calculate different vegetation indices. And then essentially, we're trying to measure how green particular pixels are. So this is just one particular vegetation index that we're also going to try out and incorporate into our estimation approach. So here's my second math slide that I warned you about. So I've got my Y here. So this would be my above ground biomass estimate for the entire stand. So we end up building in two models here. So we've got predictions from our wall-to-wall model. So that's the model using just this little X here would be our what is it? Our drone data. And then we take an average of our predictions over the entire grid. And then we do a couple different bias corrections based on this submodel. This is the model that actually incorporates that terrestrial laser scanner data, the variables that we calculated from there. And then we just have these two additional bias correction terms to make sure that our estimator is reliable. Then we can estimate a variance using this nasty thing, and then we can get our standard errors from there. So we tried out a few different approaches. So we tried our traditional design-based approach where we just used our 10 FIA plots. And then we tried a model-assisted approach with our 10 FIA plots and then a regression model relating to that vegetation index. And then we tried our two-phase estimator. So this is the one that ends up incorporating that TLS data, the terrestrial laser scanner data. And then we also had an estimator that incorporated the TLS data and the vegetation index data. And then these are estimates of above ground biomass density in tons per acre using all four of these approaches. And you can see that the standard errors are pretty high in the design-based approach. And then we do get a little bit of benefit from bringing in that wall-to-wall vegetation index, but we do get we get a pretty significant reduction in standard error when we actually bring in that sampled TLS data. And then if we can use both, we even get a hair better. So this is just one idea about, potentially figuring out a way for a small forest landowner to be able to incorporate some additional data that they might be able to collect a little bit more cheaply to be able to improve their estimates. I keep saying that this thing is cheap, but that instrument is not cheap. That TLS instrument is about $40,000. So usually when I talk about this type of study, I say in the future, there will be something that will probably be able to collect this data cheaper. But actually that is happening now, apparently. The new Apple iPads actually have LiDAR scanners built into them. And I think Eli ended up posting a paper that we ended up finding them actually testing out the Apple, the iPads to be able to do these types of terrestrial laser scans that we were doing with this instrument. So we bought one, and now we're playing around with it, because bringing a $40,000 instrument down to, you know, a $1,500 instrument would be a dramatic improvement, and definitely make this type of approach more feasible for smaller forest landowners. Yeah. And then just a quick analysis on sample size here. So remember, we had 10 field samples when we were looking at the field data alone. So with those 10 field samples, our standard error was, I think, 9 or so. So this little calculation here lets us figure out how many how many field samples we would have actually had to collect to be able to get a standard error, get that 2-phase standard error. And then it ended up being about 32 plots. So we were able to get an estimate that would be the same as collecting 32 FIA plots using only 10, but then incorporating all of this, terrestrial laser scanner data. And with that, I think it gets me up to time. I imagine maybe there's an additional question or two.
Yes, there is. For now, I'll ask it and then worry about screen sharing. But
okay.
Question is, some tree species have very different wood densities, resulting in different carbon densities depending on species composition. How do remote sensing approaches correct for species composition?
So I guess when I think about different wood densities and species compositions and things like that, that's attempted to be accounted for, I guess, in the species-specific allometric equations that are used to calculate the FIA estimates based on the field plots alone. In a sense, with these models, they're basically just regressing on that plot level biomass estimate. Those would kind of be sort of at least somewhat implicitly handled in there. But yeah, so there's the types of approaches we're looking at here don't try to explicitly deal with something like that, or try to improve upon like the actual field-based estimate that the FIA does. I mean, there's always ways to improve those field-based estimates, but we are, in these particular approaches, we're regarding that FIA estimate as pretty close to truth. So,
thanks, Chad. Next question, and the only one remaining: would TLS scanning, the data collection cost, be scalable to the extent of the national FIA program?
I know there is some work where people are looking into trying to scale up the TLS scanner. Yeah, I don't know. It's an expensive instrument, and it's definitely heavy. But I think with instruments getting smaller, and as far as like, you know, something like an iPad or something like that, being able to collect this auxiliary data, it would be really interesting to see like how fast. Well, I mean, so with the FIA, they're collecting tons of data on these plots, and it takes like I don't remember exactly what the estimate is. I know the estimate of how long it takes in Alaska because I worked on that one a little bit, but it takes a really long time to collect all the data you need on a particular FIA plot, whereas you can scan a plot in 10 or 15 minutes. So the idea being like maybe we keep measuring FIA plots on our 5 or 10 year rotations, but then we can actually go in and collect this laser scanner data on the plots maybe that we are skipping over particular panels. So we can kind of incorporate that auxiliary data into these FIA estimators. I think there's a way to make it scalable, but we just have to buy a lot of iPads and figure out how to use them.
Yeah. All right. Why don't we do one more question, and I'll go to this one next. Discuss the other remote sensing technologies you'd like to see in the future. Think operational, not the free stuff like Landsat. Other technologies would be hyperspectral, high-res aerial cameras, multiband radar, and LiDAR. Any thoughts on that, Chad?
Yeah, so when you're talking about, yeah, so rather than looking at more satellite-based stuff, we would be talking about maybe stuff collected from airplanes that maybe isn't necessarily doesn't necessarily cover the entire United States or things like that. Being able to like augment, add data, essentially auxiliary data for a particular stand or county or state even, the statewide LiDAR system. But it can definitely be incorporated. It's not too terrible of a step to be able to bring that type of information into these types of models. And in fact, we essentially did quite a bit of that with the Cloquet Forestry Center there. I have played around with hyperspectral data a little bit. Hyperspectral data, I think it has a lot of potential for discerning different tree species and things like that, but I haven't seen a lot of good work as far as like trying to get at forest carbon or biomass with it. It doesn't really get that third dimension. It just gets a whole lot of essentially color information. So looking more at like LiDAR or radar type data to be able to get at that height information. At least as far as trying to map forest carbon, I think is a better bet than hyperspectral data. But if we can start teasing out different species with this hyperspectral data, we might be able to build more species-specific models and be able to, hone in on matching those FIA estimates a little bit more.
All right, thank you, Chad. I want to quickly just note that the continuing ed credit link, I just posted it for the second time in the chat, so you can look for that. And with that, Matt, I'll stop sharing my screen and hand it back to you. Thank you, Chad.
Thank you.
Great. Want to thank you all for joining us this week as a part of this webinar series. As you can tell, with such interest in forest carbon and where we're going with that related to forest carbon markets, related to how trees can play a role in a natural climate solution. We learned this week about how technology can help with that. And so really appreciative of all the folks that presented this week, especially Chad. Chad, we give you a big thank you and a virtual round of applause as well. Like Eli mentions in the chat, we've got the recordings for these 3 webinars that you'll see at that link, and encourage you to go visit that if you want to check out some of those webinars if you missed one this week. So with that, we'll sign off. Thanks again, Chad. Thanks everyone for joining us this week.